Good morning, sir. We will
Hello,
start the meeting in
am I
2
audible?
minutes.
No problem. Yeah.
A very good morning to everyone. Today, we have the privilege of being in the presence of a distinguished academic and researcher in the field of power electronics. It is my great pleasure to warmly welcome Professor Shantanu Mishra. He is currently a professor at the Center for Applied Research Technology, IIT Delhi. He has had a long and impactful career. He completed his BTech in Electrical Engineering from the College of Engineering and Technology, Bhubaneswar, in 1998 and went on to earn his MTech degree in Energy System Engineering from IIT Madras in 2000 and PhD degree in Electrical and Computer Engineering from the University of Florida, Gainesville, USA in 2006. His research interests lie in multi-phase DC power conversion, power management circuit, and the modeling and control of power electronics systems. Professor Shantanu Mishra has held key industry roles, including a senior application engineer at Infineon Technologies in Rhode Island, USA, and has contributed significantly to academia as faculty member at IIT Kanpur from 2008 to 2023. He has been recognized with multiple awards, including Best Paper Award at the Annual Conference of Industrial Electronics Society and invitation to speak at prestigious international events such as Fifth Indo-German Frontier of Engineering Symposium and the International Power Electronic Conference. A respected associate editor for several leading journals in his field, Professor Mishra's work continues to influence both research and industry, particularly in the area of energy systems and power electronics. Thank you, sir. You can start your lecture now.
Okay, so I'll share my screen. Am I audible? Okay, so I'll share my screen and then go ahead. Okay, so hopefully my screen is visible now, and my presentation is visible. Uh, just say yes. Okay, all right. So today, what I will do, see the theme of this particular congregation is renewable energy, right? So what I thought, in fact, that is what Professor Singh I was discussing. How can I bring this charging infrastructure into this renewable sector, right? So that is what I was kind of trying to contemplate with her. And then what we thought was that I should give a perspective of how EV charging infrastructure get into microgrids. So if I can establish that relation, then I think I will solve my purpose of this particular talk. So what I will discuss today is three things. Okay, like when we design power converters, what are the challenges involved in power converter? Not in terms of designing and what component to use. No, in terms of how it kind of interfaces with the grid system. What are the challenges that we face? Then the second challenge I will talk about is like when we talk about smart grid, what does this mean actually? Smart grid, what does that mean? Uh, uh, like you might have heard this term called microgrid, right? So when I will talk more about it during the talk, but I just want to give you a perspective of where I'm coming from. So when we say that we have a microgrid, we say that there are some renewable sources, some batteries, and so now there is an island. It's kind of an island in which load and sources are together. Now, set of homes, right? So for that kind of a thing, it is okay that the new home is built, and whenever it was being connected to the distribution grid, you connect it as a microgrid. But what happens to places where the grid is already established? Because 90% of our distribution grid is already established. So when I'm talking about distribution grid, you should understand that I'm talking about our homes. Our home is connected to this 230-volt system, right? So that is what I'm kind of talking about. So all these systems are already established. So here, how do you develop a microgrid? Was my question to them. So in fact, there were some answers that I got, and I actually published those answers in IEEE. So those things I will kind of discuss. And this is very much related to EV charging infrastructure. But because when you are talking about home, you are actually talking about EV charging infra also, right? Because in your home, if you buy a EV, then you will be having EV charger, and then that EV charger is also a part of your home now, right? So it is also a part of your smart grid. So these three concepts we will kind of discuss, and we will see what are the problems in that. So it will be a little bit confusing, but I mean, ask me a lot of questions, then you will understand that these are all distinct subjects of interest where people will do research, and there are a lot of gray areas in that and a lot of openings also to develop new solutions. Okay, so when we talk about a renewable system, there are two types of renewable system we actually talk about. Even though that is not explicitly said, but this is precisely what we do. High power system and low power system. So high power system is, let's say you have a big solar farm. Okay, so then that solar farm is connected to the big grid. Let's say you are generating 500 kilowatt power through your solar farm. Then obviously you are not going to connect it to your distribution transformer, which is like a 100 kilowatt distribution transformer, right? The transformer that is near to your home is what I'm calling as distribution transformer, right? So, but rather you will be connecting this 500 kilowatt to a substation. Okay, so substances is at like 13 kV or a little bit higher than the 33 kV kind of a thing, right? So that is called a high power system. And this high power system, the characteristic of this high power system is that they are always balanced. Okay, phase A, phase B, and phase C, they will all carry the same current. Okay, in India it is true, in US it is true, in Germany also it is true. Okay, uh, but when you talk about low power system, that means my home having a rooftop, then that rooftop is generating a AC. That AC is probably used in my home, or you are actually grid connecting it and selling power to the distribution grid. So there, whenever you are talking about a low power system, then there are a lot of challenges in this low power system. The reason there are challenges is that our low voltage distribution grid is actually highly unbalanced. Okay, you think about your home. So you might have heard about our mom saying that, oh, hamara phase power cut ho gaya hai, right? Hamara phase chala gaya hai. So what that means is that there are three phases. Okay, phase A, phase B, phase C. Your house is supplied from phase A and ground. Someone else's, your neighbor's house is supplied from phase B and ground, etc. Right now, it is possible that one of the phases is gone and the rest of the phases are working perfectly. So what that means is that our distribution grid, that low voltage distribution grid, is highly unbalanced. In India, it is especially true. In US and Germany, it is never true. Okay, in US and Germany, the low voltage systems are highly balanced as well. Because I was asking one of my German friends, have you seen a power cut ever in your life? He said that, what do you mean by power cut? I said, power going out. I mean, the AC, the supply going off. He said, how can the supply go off? I mean, he could not comprehend that the supply can go off. Okay, he could not comprehend. And that is absolutely unheard of. Let's say when I am talking to you, right? If I say that, have you seen a power cut? I say, मजाक कर रहे हैं क्या? Power cut देखा नहीं, आज अभी तो हुआ था हमारा. Right? So we are used to power cuts, but they are not used to. For them, the low voltage distribution grid is also balanced. For us, the low voltage distribution grid is not balanced. It is highly unbalanced. Okay. And why am I saying you all these things? Because our EV charger, okay, is actually connected to the low voltage distribution grid. It is not connected to the high voltage grid. Right? It is actually connected to the low voltage distribution grid, because we will have a 50 kilowatt charger or 100 kilowatt charger. These are all within the power rating of the distribution transformer that we are having. Because our distribution transformer in Prime Minister Yojana, they are giving 66 kilowatt or 100 kilowatt distribution transformer, or a little bit higher than that. So that is the distribution, the power rating we are actually talking about, right? In our low voltage distribution. So till this point, do you have any questions I can take up, or I can go for? If you have any question, just put it on the table. We have to talk through it and then go forward, because small doubt remains in your mind, then it will always remain in your mind. And if you are shy like me, I am also, I don't ask questions. So you can put it on the chat box. I will try to answer. All right. So I will just hold on for 10 seconds and ask you if there are any questions. I can take it up. Otherwise, I'll go. All right, so let me go forward then. So this low voltage business, low voltage business means rooftop business that you will be knowing as, or I will be knowing it as small power microgrid or nanogrid. Okay, so these systems are actually becoming prevalent now. In fact, MNRE has a scheme where 2 crore grid connected inverters are supposed to be implemented in India. And you will not believe all these businessmen are actually going to China and buying those 2 crore inverters. 2 crore inverters they are buying from China. Okay, and none of our Indian companies are able to compete with that because we cannot just simply compete with their price. All right, so so that is a big business. Okay. Uh, the intention of the government is actually good, that they want to promote Indian manufacturer, make these inverters, but uh, we have not delivered. I will say that we as academicians and researchers have not delivered, and of course our business community has not delivered. Okay, uh, but you can see that there is a lot of business in that area, right? 2 crore inverters, small inverters, rooftop inverters will be installed in the next few years, right? So now when you are talking about these inverters, so this is a part of the low voltage microgrid. Okay, low voltage. That means these inverters will be connected to the distribution grid. That is 440 volt three phase, right? Uh, so that so how do we connect that? Actually, there are 3 methods of connecting that. So we will have a PV or an inverter with a line transformer, okay, or PV with a high gain inverter, high gain inverter. There will be no isolation here. And the third one is a PV with a boost converter and an inverter. Actually, the first method is the most preferred one because there is a line frequency transformer between the PV and the grid. Okay, and most of the imports that are happening right now in this rooftop business, inverter business, is actually either the method 2 or method 3. So there's no isolation there. So from China, they for some reason, some European has made a calculation that it will not get a shock, and these guys, without even thinking, are thinking that there will be no shock, and then they are basically buying inverters that do not have isolation. Okay, but in my point of view, in India, if you want to implement anything, that needs to have isolation, because Indian ground is in India, the ground, the earthing is not that great. So therefore, we have to be very careful while implementing higher power 3 kilowatt, 4 kilowatt system with higher voltage. So normally, when we are talking about 230 volt, we are actually talking about high voltage. Even your laptop charger and cell phone charger has isolation inside them. So obviously that their isolation should be there. But all the imports that are happening right now in this inverter sector for the 2 crore inverter business is a non-isolated one. But I think that there should be isolation there. Anyway, that's not the point. Point is that this is a big business. And why am I saying you all this? Again, I'm saying you all this is that instead of the PV, you just replace it with a EV. Then you have a rectifier now. Now the same EV is now taking in power from the grid. So in PV, the power is being given to the grid. In EV, the power will be taken from the grid. The challenges are the same, right? So if you think about power electronics, there are 4 types of power converters. Okay, so without going into detail of what is inside them, there are 4 types. The first one is a DC to DC converter. Second one is a DC to AC, like our home inverter that we have, or any solar inverter that we have. Solar is a DC voltage, and we are getting AC voltage out of it. And then we have a rectifier, which is like our laptop charger kind of a thing. So you give a AC, and then you have a DC power. The EV charger falls into this rectifier category, and then there is a AC to AC converter. AC to AC converter is no longer cyclo converter, they used to call in olden days. They are no longer used anymore. Actually, if they want a AC to AC converter, they actually put a rectifier and an inverter in cascade. If you put this one, D and B in cascade, you actually get a AC to AC converter. And that is the example of that is in our uh, uh, washing machine, we have variable frequency control. Our washing machine, that motor rotates in one way, another way, something like that, right? So this clockwise, counterclockwise rotation is actually achieved through a AC to AC converter there. So there you have a rectifier and a inverter in cascade, so that they can do V by F control. Sorry. So now, so now if you look at any power converter, no matter which power converter we are talking about, it will have two distinct stages. One is a power state, another is a control stage. So the job of the power stage is to process power. That means that when you are saying that my power converter is of 3.3 kilowatt, then you are actually talking about the rating of this power stage. All the switches, etc., are 3.3 kilowatt, etc., right? And when you are saying that my power converter can supply me 5 volt or 10 volt or 230 volt or 110 volt, then actually we are talking about this control system. This control system is the one that is actually maintaining that voltage for you. Okay, so let's say in India, if you are designing a grid connected inverter, a solar PV inverter, then my voltage here at the output, my voltage at the output, let me just put it as a pointer so that you can see. Okay, so at the output here will be in India it will be 230, but if you are doing it in US it will be 110. So that is decided by this control stage. Okay, I'll stop again here, and if you have any questions I can take. So far, if you have any questions, please ask me. Don't hold back. No? Please don't hold back. Just ask a question. That's it. Okay. All right. Hopefully, you guys are awake, and that is my only hope. Because I cannot see you, so. Anyway, so now, like when you talk about any power converter, so for seasoned uh, converter designers like me, for me, an inverter and a rectifier are no different. They are the same thing. All right. So when we think about any converter, we see the converter in terms of the power rating. Okay. So for me, a inverter and rectifier are not different, but a inverter which is 3 kilowatt and a rectifier which is 100 kilowatt are different. So kilowatt is our main differential factor, not the type of converter. Because for the type of converter, every converter is kind of similar to us. The switches, inductors, they are connected in a certain fashion, but the technology is what is very important. So the technology is that when you are actually going for very high power implementation, like HVDC kind of implementation, you technically need to have a very low switching frequency. Normally the switching frequency is about
Sir, PPT is not showing.
Is the PPT visible?
Not visual, sir. Okay.
So there is a
Now I just took it off, but now it should be visible. Is it visible now?
yes, sir.
Yes, sir.
Okay, Ranjit ji, can you check? Okay, no?
Okay, sir. Okay.
All right. So, okay. So, see, normally when you go for very high power implementation, you need to have a very low frequency, right? So normally it is below 500 hertz or something. Okay, and then as your power rating actually goes down, your switching frequency need to go up. Like for example, consumer electronic devices in your cell phone, whatever converter you are using, the converter switching frequency will be extremely high, like megahertz. Because when you are actually the reason this is done is that one thing is loss, second one is the magnetic size. So magnetic size will be far smaller when the switching frequency is high. So therefore, it will be light. So consumer electronics need to be light, right? Because we are moving around with our cell phone. The lighter it is, the better. So therefore, we need to have a very high switching frequency there. And let's say we are designing let's say 100 kilowatt converter, then we are actually going for something like a 50 kilohertz or 75 kilohertz, something like that. But when we are going for, let's say, 1 megawatt converter, okay, which is there in the HVDC system or very high power, let's say bus charger, okay, electric bus charger, right? So there you need to have a switching frequency which is actually low. Okay, so this is basically telling this graph is that as your power rating of the converter goes up, your switching frequency inherently has to be small. Okay, because otherwise you cannot meet the efficiency numbers that are there. All right. And this is the map of when to use what. Mostly what happens is that at very high power we will either prefer a thyristor or BJ or IGBT. At like a little bit higher, little bit lower power level, at 100 kilowatt level, we will actually go for something like a, put the pointer in. Okay, I'll go for something like a IGBT or silicon carbide device, or like when I have even smaller power, 10 kilowatt, 20 kilowatt, 30 kilowatt rating, there I will have hundreds of kilohertz, is okay, and then I will have MOSFETs as my rating, and then at very high power, very high switching frequency I will use when my wattage rating is very small, like 10 watt, maybe 5 watt, or maybe 1 watt. That kind of a converter, I will have a switching frequency very high there. All right, and they are mostly the devices that are chosen are GaN devices. So you will see that Texas Instruments is one of the leading designer of GaN devices, because they are actually focusing on consumer electronics. Right. All right, so when you look at an inverter, so when we say that it is a voltage source inverter, the general feeling is that it is called a voltage source inverter because the source is a voltage. No, actually it doesn't matter whether the source is a voltage or not. We are actually concerned about this voltage here, output. This is a voltage because when you are switching it, you are actually having some pulsating waveform here. Okay, so let me see if I can draw here. All right, so we will have pulsating waveforms here like this. Okay, so there is like this and like this, like we have pulsating. So this terminal here is actually directly connected to a voltage source. So therefore the voltage here, the magnitude of voltage here is directly dependent on this voltage. So therefore it will be called a VSI, voltage source inverter. So if you actually, in fact, the counter argument is that if you actually put the same source with an inductor, actually it becomes a current here. So therefore, when you switch here, you are actually switching a current, because this current is now switched, because it is ultimately what is this switching structure viewing is what is important. The switching structure is viewing a voltage source here, and if you put an inductor, then it is viewing a current source. So therefore it becomes a current source inverter. The general thought among researcher is that this is a voltage source, that is why it is called a voltage source inverter. But in current source inverter also a voltage is actually used. Okay, but there is and externally you have to put an inductor. So as far as source is concerned, it is still a voltage source. So why are you calling it a current source inverter? The reason you are calling it a current source is because the switching structure is actually seeing a current source. Okay, so you have to be worried about what this switching structure is doing. So whether it is doing a current source here or a voltage source here. All right. So and these are some of the formula. We will not use this formula, but I just wanted you to know this voltage source and current source, because this is important, because we are actually connecting it to the distribution grid here. Right. So now one of the important concepts that you should know here is that like, if you are using a voltage source inverter, your output is a voltage. So now output is a voltage, and you cannot connect it to the grid, which is also a voltage directly, because then you will be shorting two voltage sources. So therefore an inductor has to be there in between. So therefore in any kind of inverter, there will be a inductor here, and there will be a small filter here, then there will be the grid. So that is the reason this inductor is actually essential. We think that the inductor is essential for filtering it out. Yes, it is filtering out, but this is actually mandatory. Without that, you cannot short one voltage source with another voltage source. All right. So that is one of the things that I thought that you should be clear. Right. So now in inverter, so there are like these are the challenges of designing inverter, right? So we have a DC voltage, and we are actually trying to like generate a AC voltage here. Okay, so let's say some impedance is there. So if there is some impedance, then VI cos phi you can do and then find out the power, right? So then there will be active power and then there will be reactive power. So then my question always I used to ask, what is this reactive power? What the hell is this reactive power? All right. So we know that active power balance is always there. Like for example, in this case, if I want to find the input current, DC value of input current, then the DC value will be equal to the active power divided by 48. That will actually give you the DC current. Okay. But what happens to the reactive power? Is there any reactive power balance? So like I'm saying that there is a DC voltage, therefore there is a DC current. So therefore this input power will be equal to the output power. When I say input power equal to output power, I am actually talking about input active power equal to output active power. All right. So now that is kind of visible. That is kind of obvious. Now the question is, what happens to this reactive power? Is there any balance of that? That was one of my questions. And why this question was important? Because actually, if we don't answer this question, then we cannot design the inverter. Okay. So that is why, in any inverter or rectifier, this question has to be answered. What happens to the reactive power? So if we go forward, so just hide this thing here. Okay, go forward, then there is a reactive. What happens to the reactive power balance? Do you understand this point that I am trying to make? Active power balance and reactive power balance. Is it okay so far? It's a simple basic electrical engineering, right? So we have an input voltage, a DC voltage, we are generating AC voltage, then there is impedance. So what is the active power and reactive power? So from that active power, you can actually find out the input current, DC current. Okay, now what happens to the reactive power? This is what the question is. Did you understand this concept? I can go forward if you have understood. आप सब लोगों ने मौन व्रत ले लिया है, क्या करें? ठीक है, so to say something, say something. I cannot see you, so I cannot make joke, right? You have to say something so that I know what you are thinking. And anyway, so like if we want to draw the voltage and current of this waveform, it will look something like this. There is a voltage and the current is phase shifted. So if you multiply them, then that will be the apparent power, and then average of that is the active. Okay. So always, like when you multiply the voltage and current at a certain terminal, that it will give you a oscillating component. The average of that will be your active power, always. Okay. No matter what the voltage waveform is, no matter what the current waveform is. So if the voltage has harmonic, current has harmonic, voltage is nonlinear, current is nonlinear, don't worry about it. At a terminal, just multiply the voltage and current for a longer period of time and average it. So that will be your active power. All right. So now, like this will be the phase, phase of that. Like voltage is here and current is at theta angle, right? Now, when we are multiplying them, we are actually getting P and JQ. Okay. But if you remember, then what is this thing called? This is this called power phasor or power triangle? This you remember this thing, right? P and JQ. So is it called a power phasor or power triangle? Remember your undergraduate? What is this thing called? Basic electrical, it was taught to you. Tell this, no? What is this thing called? This is the phasor, right? Voltage and current phasor. But when we do the power calculation, we actually draw this curve here. S is equal to VI, then P, then Q, then S equal to P plus JQ. Okay, where P is the active
Sir,
power.
this is apparent power, sir. Yes, इसका apparent power.
S apparent power है और P एक है Q एक है, सही है ना? ये सही है ये?
जी.
हाँ, तो इसको क्या बोलते हैं? इसको
Yes, sir.
इसको क्या क्या बोला जाता
Power
है?
triangle.
पावर ट्रायंगल बोला जाता है. इसको पावर फेजर नहीं बोला जाता है. क्यों पावर फेजर
जी.
क्यों नहीं बोला जाता है? Why do they call it power triangle, not power phase? Why it is called? My question to you is that you have absolutely rightly pointed out that this is called power triangle. Why it is not? Why not power phase? Power phasor. इसको तो वोल्टेज करंट फेजर बोल जाते हैं. This is the phasor diagram, right? So why this is not called a phasor diagram? ये मजेदार चीज है actually. Very we do it every day, but we kind of ignore the basic things. Like I also ignored it for a long time, and later on, one of my students actually taught me that this is why it is not called. तो ये क्यों ये बोला जाता है पावर फेजर? मतलब पावर फेजर क्यों नहीं बोला जाता है? इसको आप कुछ इसमें कुछ आइडिया दे सकते हैं क्यों क्यों नहीं बोला जाता है पावर फेजर? ओके, हाँ, बेझिझक बोलिए. कोई आई ऑल्सो डोंट नो हाफ द थिंग्स, डोंट वरी. You know, like over a period of time, you deal with very good students, and it's a rub-off effect of their knowledge on us, right? So over a period of time, we have become smarter and smarter and smarter. But to start with, I don't think I knew half the thing that I am talking about today. Not even half. I mean, I've told you 10% of the things. Right? So फेजर डायग्राम का फंडामेंटल क्या है? ये फेजर डायग्राम क्या होता है? What is the fundamental of a phasor diagram? When do we draw a phasor diagram? When we draw a phasor diagram, when the voltage and current are actually rotating at 50 hertz, 50 cycles per second. Remember this? फेजर वही होता है जो 50 हर्ट्ज में रोटेट करता है. पावर और Q, P और Q actually rotate नहीं कर रहा. P is a average value, Q is also a some value. They are not rotating. They are not changing with as a function of time. That is why we cannot call it a phasor. We actually call it a power triangle. But the most important thing here that you will figure out is that वो जो Q होता है ना, जो this Q that we are talking about, it is a absolutely fictitious quantity. ये लोगों ने इन्वेंट किया है. ये कोई कुछ नहीं होता है Q बोल के, कुछ नहीं होता है. इसको इन्वेंट किया गया है ताकि we can explain what problem is happening, right? So उनको पता है, people when initially go 200 years back. So when they said that there is a voltage, there is a current, they multiplied it. They thought that is power. They call it apparent power, like you pointed out. But then they said that, okay, if this is apparent power, how come my consumption, like at my load end, my consumption is only P, is smaller than that value. ये तो सही बात बोल रहे हैं आप. तो then they said that okay, let's define this power called P, active power इसको बोलेंगे. Now, once they defined the active power, they had to define something else because otherwise it is not matching with that S. So then they defined something called reactive power. All right. So reactive power is actually a made-up quantity. It is actually absolutely a made-up quantity. So now I will explain you why it is a made-up quantity. देखिए, like whenever we are teaching reactive power to kids, okay, you must be teaching that. तो आप क्या बोलते हैं कि active power is the average value, reactive power is the power that is going back and forth. Is what we were talking about. I am actually questioning that thing now. So let's say there is a resistor and there is a voltage V sin omega t, I sin omega t. तो आप multiply कीजिए, आपको एक average power मिलेगा और एक oscillating component मिलेगा. Okay, एक oscillating component आपको मिलेगा actually. So is this oscillating component reactive power? No, obviously not, because we have only a resistor. There is no inductor there. Then what is this oscillation going on? So this oscillation is actually called oscillating. Right. So we have a reactive power. We have
sir, one is 0.5 constant power and Instantaneous power 0.5 VMIM cos.
हाँ, so one is instantaneous. So वो reactive power नहीं है, is what I am pointing out. So this will be your
One is constant power.
हाँ, this is called oscillating power. So this is not reactive power. This is called oscillating power because there is no, there is a resistor. There cannot be any reactive power here. Okay, this is called oscillating power. है ना? So इसका like I am summarizing it here. Let's say आप Vm sin m omega t है और phi उसका phase difference है. So suppose like the phi is 0. Okay, then you will see this kind of a waveform. Okay, so that will be called a pulsating power. This will be called a pulsating power, and then the average of that will be called the active power. And when the phi is non-zero, then you will have something in the it will go in the negative direction. That means power is flowing this way and this way. In this one, power is not flowing opposite, right? Power is only flowing this way. It is becoming smaller, greater, smaller, greater, but always the direction is positive. Zero is here. So therefore, this will be called a pulsating power. And whenever there is a negative, that means power is flowing this in a larger instant, and for a smaller interval it is flowing in the opposite direction, then only it will be called a reactive power. All right, so why am I mentioning all this? Because actually if we don't have an understanding of this, then we cannot design the capacitors and design the inverters here. Okay, because our job is to make sure that every aspect of that power transfer is accounted for. Okay, and this reactive power, whenever it is going in the negative direction, this reactive power is accounted for by a capacitor here. So in other words, what we are basically saying is that when you have a solar panel, okay, so you must have like done research on solar panel and things like that, and people will put an inverter here and connect a grid. So whenever they are doing that, they are actually doing it wrong. The reason that they are doing it wrong is because whenever you have a solar panel, you have to have a capacitor outside. Okay, because that capacitor, if you don't put, then who will take care of this negative power transfer? Because when the negative power flows here, if you do not have a cap, it cannot flow through the solar panel because the diode is already there. There is a diode in series with that solar panel. So this is one of the things that I have seen many theses will do this thing wrong, right? So that's why all these things have to be accounted for when we are designing this inverter, as well as when we are drawing this kind of pictures. Okay. So to summarize, what I'm trying to say is that next time when you put a solar panel and an inverter, okay, and a grid, actually this picture will be a wrong picture because if you do not put a capacitor here, it will not take care of the reactive power, and reactive power is actually there. You cannot avoid it. Okay. You will be having some kind of a reverse power flow, so that has to be accounted for by this capacitor. All right. So far so good. Is it okay? Okay, buddy.
Yes, sir.
Okay. All right. So in low voltage system, when we are saying low voltage system, actually we are talking about systems which have let's say a input of 48 volt kind of thing. Okay. Because like homes, like normal homes, like I want to buy a solar panel, I don't have infinite fund like government of India. गवर्नमेंट ऑफ इंडिया के पास राजकोष है, मेरे पास थोड़ी राजकोष है, मेरे पास थोड़ा सा छोटा सा बैंक अकाउंट है. So I will buy a small panel. So therefore, in low voltage systems, we are constrained by the financial constraint of the people who are buying those solar panels, right? So and normally because of financial constraint, they will buy only 1, 2, 3 solar panels, right? So the voltage will be actually low. In India, that will be especially true. We are not talking about American system or European system. We are talking about our country. So from next time onwards, when you think about a problem, always think about your country. You don't have to think about America. You are not staying in America. You are not staying in Europe. You are staying in India. So whatever problem we have to solve for us, not for anyone else. All right, even when you are giving a PhD subject to your students, do that, because our job as a taxpayer is to solve our problem, not to solve their problem. All right. So now this inverter is actually like this has a very small voltage. Now, depending on the power rating, it will have some current, input current. So let's take this example. So let's say we have a 48 volt inverter, 10 kVA 48 volt inverter supplying power to a 440 volt three phase system. So if you do that, then your input current will be 200 ampere, because 10 kVA divided by 48 will be around 200 ampere. Okay, but output current is only 13 ampere. Okay, so this is a very bad thing for us, because 200 ampere flowing through a wire will create a lot of I square R loss. You will not believe how thick the wire will be. So this is not a very practical system. So therefore, by design, okay, this if you go higher in power rating, your voltage also has to go high. Let's say you want a 10 kVA inverter, then it cannot be 48 volt. It should be something like 200 volt or 400 volt. Then only the current will be at a level where the losses, etc., can be managed. This is the practical constraint. It's not a theoretical thing. See, the great thing about power electronic engineer like me is that we cannot hide behind equation. We cannot just say write a equation and say that it is possible or it is not possible. We have to design the inverter. I like as a part of my lifestyle, I have to design the inverter. I have to prove it in an actual system. So 200 amp is something that will create me a lot of problem when I am designing it. So the take home message of this particular slide is that as your power rating goes up, your input voltage also has to go up. Otherwise, it will be a big challenge for you to take care of the current. All right. So therefore, at our home level, if you are putting a rooftop panel, then the rooftop panel will have a voltage of, let's say, 48 volt. The rating will be about 1 kilowatt, 2 kilowatt, something like that. It cannot be 20 kilowatt, 50 kilowatt, right? So the reason that is true is that the input current will actually make a difference, right? In fact, I'll come back to that MNRE guidelines that has been provided for grid connected inverter, for that 2 crore inverter that people are buying. So there they have mentioned that it should be somewhere between 2 to 3.3 kilowatt. Okay, so that is though they have not specified any voltage, they actually have specified, but it may not be the voltage. Anything can be there, but 3 kilowatt is your is what they are actually looking for. Right? They have mentioned the voltage rating, by the way. I'll be wrong if I don't say that, but it doesn't matter, na? 3.3 kilowatt, if you can make it with a 48 volt also, it's fine, because at the end of the day, you need an inverter which can be put on a rooftop, right? So now this will be all about the power converter challenges. So I just gave you an overview of what are the challenges that we face in power converter design. Okay, so when I say power converter, I'm actually talking about inverter as well as rectifier. Inverter is for let's say solar kind of application, rectifier is kind of EV charging application. For me, they are actually the same thing. All right. So now let's go to the smart grid. So like I was talking to you about, like if you this is a very important picture here. So when people talk about distribution grid, especially power system people, many of you may be power system guys here. So when people talk about distribution grid, they actually hide behind this high voltage or medium voltage distribution grid. Because this high voltage and medium voltage distribution grid is actually exactly similar to a transmission grid, because it's absolutely balanced. This distribution grid is very similar to this system because they are balanced. But what is challenging in distribution grid is that if you can take care of things here, low voltage distribution grid, which is highly unbalanced, highly, like I was giving you example, right? मेरे घर में power है, मेरे side घर में phase चला गया मतलब there is unbalance, right? Phase A is there, phase B is there, phase C is missing. Okay, so this is highly unbalanced, and this is one of the major challenges that we have to solve as a country, because Westerners are not going to solve it for us because they have never seen this problem before, right? So therefore, all the solutions of rooftop has to be solved here. So this is what we actually took as a challenge few years back, that how do you integrate a microgrid into a smart distribution. So now we have done a lot of research on microgrid. Now how do I apply it to a distribution grid, right? That was what the question was, right? So the answer was something like this. If you look at the distribution grid, it is when characterized, this grid is characterized by small inverters. It is not, there is no big inverter, like 3.3 kilowatt or something like that. That was what I was kind of talking about, grid connected micro inverter kind of a thing. And not only one, there will be numerous, because you can think that in a distribution grid, how many houses are there? In your locality itself, there will be 100 houses. So from 100, if the 50 of them put solar inverter of 3 kilowatt each, then you are already putting 3 kilowatt times 50, which is equal to 150 kilowatt, right? 150 kilowatt you are kind of injecting into the grid. So many small inverters will be connected in this distribution grid. And when I am saying inverter, charger will be the same thing. But many people buy EVs, then this same problem will be there for the distribution grid as well, right? So now once you have done it, now how do you take care of this? So this like we have to have some way of integrating. So we know how to integrate an inverter into a grid, but how do you integrate the grid into the smart distribution system? So that is what the question was. So if you, these are some of the definition of microgrid. I obtained it from some paper, right, from Bloomberg Energy something, right? So there they are saying that what is defined as a microgrid. Microgrid means everything inside this microgrid has to be self-sufficient, and they should be connected to the grid at only one point. Okay, that is one of the major point of view that they actually give, that it has to be connected to the main grid at one point. But if the grid goes away, okay, this system inside has to be self-sustaining. That then only it becomes a microgrid, right? So now how do I make my distribution grid a microgrid? Let's say that is the question. Then how do I do it? Like if you think about it, like what is your transformer? Your transformer is a delta star transformer. It is very close to your house, right? It is this transformer I am talking about. This transformer here. So this is a radial distribution system. So we have a 11 kV coming from the substation. You are converting it to 415 volt, 3 phase, and every house is connected to one phase and the neutral, right? So that is what is happening here, right? So we are talking about this transformer now. So this transformer, if you look at it, it is actually a delta star transformer that we have close to our house, right? It is generally 66 kVA or 100 kVA or something like that. So now here, like some houses will have will have solar panels, some houses will not have solar panels. You cannot force that every house will have solar panel. So because some has money, someone has money, someone doesn't have money, right? And at the same argument, the same argument philosophy, I can say that some people can have PV electric vehicles, some may not have electric vehicles, right? So but then how do you take care of that? So if they are on the same phase, there is no problem. Like if two houses are connected to R and neutral, then let's say there is a power cut and this house is generating a lot of power, it can supply to itself as well as to this particular house. There is no problem there. All right. But the problem will come when one house is trying to supply to another house. Let's say if my house is on phase R to neutral and my neighbor's house is from B to neutral, then I cannot supply from R to B. Okay, because phase-to-phase transmission is not possible in our distribution because of this neutral wire. All right, so this is actually absolutely not possible. Right. So in that case, another problem that comes is that, let's say my houses generate a lot of power. Then actually the distribution transformer right now is there that we have close to our house is actually it can take reverse power, but it is actually not designed to take reverse power. It is not. It's the transformer itself has no problem. Okay, but the equipment around it we have not anticipated that it will take power in the reverse direction. So this condition will happen when, like inside this system, there is enough power generated. Like let's say 10 kilowatt is the requirement of this particular 4 houses, but they are generating, let's say 20 kilowatt. What will they do with the less 10 kilowatt? They should be able to supply to the distribution grid, right? And here the problem is that some will be in phase A, some will be in phase B. So that is also a little bit difficult in this today's scenario. So what solution people have found out is to have tie-line converters, but that is actually expensive. All right, so you like you have to have many tie-line converters between many microgrids, right? So one of the solutions that we proposed, it is a IEEE paper. If you want, I can just share it with you. So is that you actually need to have a solid state transformer. You don't have normal transformer there. You actually have solid state transformers. So if you have solid state transformers, then actually this distribution grid from the substation becomes your highway. That means if this microgrid is generating, let's say, higher power, let me just draw it here. So let's say this microgrid is generating a very lot of power. Let's say the requirement is 10 kilowatt, but it is generating. This is the requirement, but the generation is, let's say, 30 kilowatt. Okay, this is the generation of this particular microgrid here. Okay, then what it will do to the rest 20 kilowatt? It will actually use this SST to pass it on to this bus. So once it is in this bus, it can actually, it's a highway now. It can go to there, here, or here without any tie-line converter. If you have tie-line, then it can only go from here to here. Let's say you have a tie-line converter here. But if you are using this main distribution grid as your highway, then you can actually reach to any other microgrid. So all distribution transformer replaced with a SST can now work like a proper like microgrid connecting device, right? So this was what we actually proposed in one of our papers. And it was very well received by the community, because they were making SST, they didn't know what to do with it. So we said that if you have SST, then actually you can actually replace all our distribution transformer by this SST, and it will now become a microgrid. Like all microgrids can be interconnected. All right. So if you have any questions so far, I can take it up. Otherwise, I'll go forward. Any questions so far? All right. So anyway, so next one is that now when we now we have a context of what a smart grid is and what we are doing with the smart grid. So you can easily see here that just because someone said that we will design a microgrid, we don't do it. We have to see it in terms of our country and see whether it will be beneficial for us. Okay, like I will give you this example. People will feel bad about it. Like when Chat GPT came. Okay, I remember 6 months back when Chat GPT came. The whole of India, I mean, I was surprised by all these faculties and people and all these technological. They had no end of it thinking about Chat GPT and talking a lot about how Chat GPT can improve their life and this and that. We were basically gungan kar rahe the basically, right? During that time, China was developing their own Chat GPT, and they came up with a much. So see. The problem is that we are not thinking what we need to do, because see, unless we sustain ourselves as a technological superpower, no one is going to do it for us. Okay, then everything will vanish. Okay, so if a house is built on cloud, then the house will vanish. So similarly, a chat GPT, they are saying that, okay, you write down a terminology called thesis, it will write a thesis for you. If you can write, then 10 people, other people can write, right? So that is one of the like important things people forgot. Like you can see it in Bollywood as well right now. The songs that are coming out. Let's think about Javed Akhtar writing a song, and this like currently whoever are there are writing song. I mean, you can see poetry in those songs, right? In those Javed Akhtar songs, right? So the reason is that they have put time into it. They have put energy and time into it, and each and every song will require days and days to make. But once it is made, it is like a masterpiece. People will like it's like a people ka ped hota hai. Like, the question is that whether you want to be a people ka ped or a like a gende ka phool ka ped, right? So gende ka phool ka ped 2 महीने में आएगा फिर मर जाएगा, but people का पेड़ वहीं रहेगा और रास्ता दिखाएगा, right? So right, so that like this should be our research motive. What is that is important for us? What is that is important for my society, right? That is actually somehow we have to kind of bring it to our research, and I'm pretty sure many people are doing that, but this is something that just has to be kind of thought through, right? If you have no questions, I can go forward. So now this EV charging. So EV charging. So there are like two types of EV chargers that you will find. Now the question is that, see, now we have seen that this is where the microgrid is formed. This is where solar PV is connected, and this is where the EV will be bought. The person residing in this house will be actually buying the EV. So if they are buying the EV, they will be charging the EV there. Okay, so that is why now we are coming to the EV charging thing. So there are two types of EV charger. One is DC fast charger, another is called AC charger. So DC fast charger is it is directly supplying power to the battery pack, and AC charger, it is supplying power through a on-board charger, they call it. So ultimately the power is coming from the grid. Okay. So whether the grid is directly supplying it to the battery or supplying it through a like a inverter inside, so is what is the difference, right? In AC charger, the grid is like you are connecting your charger to the AC supply. The AC supply goes inside the vehicle. There it converts into DC and gives it to the battery. But in DC fast charger, the DC is converted, the AC power is converted to DC, and DC directly gives to the. So ultimately, grid is the source and battery is the load. Battery requires a DC. So directly, either you convert it outside DC and then supply it, or you convert it on the inside the vehicle and supply it is up to us. So naturally, if you are supplying inside the vehicle, the power rating will be smaller, because our home power is actually small. It is like, what is the highest plug rating that you have in your home? 16 ampere plug, right? So 16 ampere times 230 will be your maximum power you can take. All right. So that it's like something like 3.3 kilowatt or 3.5. So if it is above that, you have to go for a special DC connection, special single phase connection or a 3-phase connection, right? So that is the difference between AC charger and DC charger. So now when you are charging, there are two things you have to be worried about. So the first one is that there is something called optimal charging. So in optimal charging, the first way of optimal charging is current mode charging, and second one is voltage mode charging. So you can easily see this in your cell phone. So when you charge your cell phone, you put it in charge from 0 to 80% or 90%, it will actually charge very, very fast. Okay. And after 90%, it will take a lot of time. The reason it is taking a lot of time is that from 0 to 90% of SOC, SOC means state of charge, which is like battery has been discharged, right? State of charge. So 80 to 90%, when you are charging, then you are charging with a current, right? So this is called CC, constant current charging. Then after that, it automatically goes into a constant voltage charging. Why does it go? Because actually as the charging increases, the SOC of the battery increases, the internal resistance of the battery actually keeps on increasing. So if I at 90%, if I go for a CC charging, then I square R loss will be there, because battery ultimately is represented by a simple DC source and a resistance, right? So if it is discharged and you are putting a current through it, this resistance is small and therefore it charges. But as the SOC goes up, this resistance also goes up. So if you charge it with a constant current, then I square R loss will be there and heat will be generated. So it will be heat generation. So this is one of the things that the BMS takes care. There is a battery management system that is there that will be taking care of this. So this BMS, when they are not properly made, you will see fire. So when you see fire in a battery, so normally you will see fire in batteries. You will hear stories about how fire has been there. So whenever you see hear about this fire, that can be because of two reasons. One is that this CCCV has not been properly taken care. When that transition will happen has not been taken care by the BMS. One thing is that. Second thing is that whenever there is a battery, there is an electrode. At no point the electrode should short to each other. If they short to each other, then also there will be fire. All right. So that generally happens when there is some kind of accident. So that is generally ruled out. Normally we have seen that just the vehicle will be there and it catches fire. That is because the CCCV charging has not been taken care properly. All right. So this is a very important concept for any battery, and that will be kind of important for any because it is important for battery, it is important for EV. And for EV, it is more important because the battery of a EV is at 30 kilowatt hour. Okay. Whereas in your cell phone, the battery is very small. I think ampere hour mein hoga, ye 5 ampere hour or something like that. Okay, 5000 milliampere hour aisa kuch hota hai. Okay. Not very big, but this is 30 kilowatt hour. Right? The voltage has been multiplied because the rating is so high. Right. That is the BMS and the battery basics. Right. So now with this, how do you make a current control and how do you make a voltage control? Right. So because we say that we have to make a constant current control and we have to make a constant voltage control. So that's what we said here, CC and CB. So how do you make that? Actually, that is made by this controller. I was talking about this power stage and controller. This controller is actually taking care of whether a converter is a current source or a voltage source. So now this is your EV. This will be your EV. This is your EV, and whether the converter here is a current source or a voltage source is dependent on what type of controller you are having. So if you are taking the voltage as your feedback, then it becomes a voltage controller. If you are taking current as your feedback, if you are taking current as your feedback, it becomes a current controller. So this thing that is taught to us when we were in basic electrical is that how do you make a current source and a voltage source. So one question one answer that is given by all my students is that you connect a big inductor to a source, and then it will become a current. So that is actually true only for AC. Okay, and that too under certain conditions. For a DC, no matter how big an inductor you put, inductor will be a short. So no matter how big the inductor you put, it does not current source. So it is generally done using feedback circuit. All right. So now, when we go to rectifier, if you have any questions so far, I can answer it. Otherwise, I'll go forward. I have 10 more slides, so maybe 20 minutes more. Then your pain will be over. Any questions? Okay. You have any questions? Someone unmuted. Okay, let's go forward. Now, when you are looking at a rectifier, So a rectifier. So rectifier AC voltage is your input, DC is your output. So there are always rectifiers will be two-stage rectifier. So all rectifiers that you see are two-stage. First one will be taking care of the rectification. Second one is taking care of the DC to DC stage. Why do we require two stage? The first stage is actually interacting with the grid. So it is taking care of the power factor, harmonic, regulation, etc. And the second part is actually taking care of the vehicle charging. So when you are talking about vehicle charging, better to go for constant current charging, constant voltage charging. What are the protocols that are there? So anything to interface the rectifier with the EV charger is taken care by the second stage. Okay. So EV protocol, it is matching, optimal charging, which is CCCV charging, isolation, it is taking care, etc. So all these things are taken care by the second stage. So if you look at how this transition from CC to CV happens, it is actually through a switch, so a changeover switch. So when the battery SOC is low, it is becoming a current source. Therefore, this controller will be dominating, and as the SOC becomes high, this controller will be dominating, right? So this is again, I have shown this picture before to you. There is a vehicle here, and then we are connecting it to directly this battery. We are directly connecting to the DC fast charger and taking power directly from there, or we can go through. We are going through onboard charger. We have already taken care of it, and inside the EV there are many converters also there to take care of the drivetrain. They call it. Drivetrain means this battery voltage has to be converted to rotational energy, right? So that is what is taken care of. Okay. So components of a EV charger. So like the components that are there are DC, like I told you that there are power devices, there are capacitors, there are magnetics, then there are control circuits. So let's see what are the challenges in each one of them. So if you look at the power switch response, like it is very similar to what we already told you that I was just telling you that mostly in EV chargers, people will go for SIC, IGBT, and MOSFET. Okay, so these are the three things that they will kind of use as power switch. Now, as far as frequency is concerned, when you are having a very high switching frequency, 1 megahertz, then your magnetic size actually reduces. You can see it here that a 1 kilowatt design with 100 kilohertz has this big transformer, but with a 1 megahertz has this big transformer. It's a very small one. Similarly, a three-phase 5 kVA transformer at 50 hertz is that big, but if you do it at 250 volt 5 like 20 kilohertz type, then it will actually become very, very small. So that is the impact of frequency on the magnetic. So that is why people actually go for very, very high switching frequency so that the magnetic size can be kind of reduced. Okay. And these are your options. So for a DC fast charger, so we, like I told you, that there are two stages, right? The first stage is the rectifier, second stage is the DC to DC converter. So the first stage we generally go for a boost, dual boost, Vienna type of rectifier, three-phase rectifier, and then in the second stage we will have a DC to DC converter. So DC to DC converter, of course, these are all names of type of topology you can have. So there are many options that are there. These are only some of the options that I am providing you. So some of the more popular topologies that you will mostly what you will see in DC fast charging is that people will use a three-phase rectifier here, PWM rectifier, and then they will have a DC link. From that DC link, they will have a LLC or some kind of phase shifted full bridge converter here. So there is a AC to DC converter, DC to DC converter, and now this converter is actually part of the smart grid now. So that is what is the important aspect you have to kind of understand. Okay, so this input stage, this rectifier stage, is taking care of all the grid codes. Grid code means what should be the harmonic, what should be the like power factor, all those code, grid code, whatever has been defined, so they will be taken care by this AC to DC rectifier. It's a three-phase rectifier because it's a DC fast charger, and then there is the protocol of this EV are taken care by the second stage. So these are some of the options. VNR rectifier is one of the more popular topology. The reason which is actually popular is because the person who actually invented it actually works for Airbus. I mean, he's a professor in Vienna, no, not in Vienna, he's in Switzerland. Okay, he's a professor in ETH Zurich. Okay, so he works mostly with a company called Airbus. Like Airbus, Airbus, they make aeroplane, right? So they have tremendous funding from European Union, and because this was his PhD thesis, he has made it very, very popular, and it's actually a good converter. Okay, so that is what has happened. So VNR rectifier is one of the more popular topologies in this business. Similarly, for DC to DC stage, we can have dual active bridge or phase shifted full bridge kind of a thing. That is the second stage. So this one is the first stage, okay, and this one will be the second stage. So this first stage was taking care of the grid code, and the second stage is actually interfacing with the electric vehicle. Okay, so we are talking about these two stages here, stage 1 and stage 2. So this stage can be a VNR rectifier, this stage can be a phase shifted full bridge. So this will be the first stage, this will be the second stage, right? So similarly, like for AC fast charging also, there are other options there. AC fast charging means is the onboard charger. They also have many options there. So these are some of the options for you. And then this is one of the more important implementation is a boost rectifier because it's a single phase. So you will use a boost rectifier and a LLC resonant converter. That is generally what is used inside your onboard charger. So this charger is the onboard charger. This is inside the vehicle actually. So these are some of the other topologies that are there for the first stage. Instead of a boost rectifier, instead of this boost rectifier, you can actually go for bridgeless PFC, semi-bridgeless PFC, totem pole, etc. And in all this, there will be a control implementation, and there will be sensors. Those sensors are normally this voltage sensors, and this controller is generally a DSP or a microcontroller. All right. So now, like if you look at the system level, now once you have made the charger, now you have to connect it to the grid. So here there is something called EV charging infrastructure, because this whole thing here is now your microgrid. Like whatever we were talking about in microgrid, this whole thing here now becomes your microgrid. Now this microgrid has to be connected to the AC grid, right? Either this way or so. There are two ways of implementing it. One is called DC distribution, another is called AC distribution. DC distribution is not that popular because it is something that I like. I have ulta. I have said ulta here. I just have to. This is DC distribution and this is AC distribution. This is DC and this is AC, right? Because this is AC bus here. So DC distribution is not that popular. So this is not that popular. So this is more popular because that is what people will kind of generally use. So what happens here is that actually all these portable chargers, DC chargers, they are actually bought out from China. So they are connected to a AC grid. So they actually generate a AC grid by putting battery there, solar PV there, and this will be your EV charging infra. This the whole thing is your EV charging infra. Right. So now all these things are connected. They generate a AC bus of 440 volt, a three phase, and then they connect that to the bought out AC chargers that is bought from China, right? So now you can now question that why are they not connecting it to this point directly? Why they have to have all these infrastructure? So this is where a very important concept comes into picture: the role of storage. So what happens is that, let's say you have a DC fast charger. So this charger, let's say, is there. So let's say that is 100 kilowatt charger, and let's say I have 5 of them. So then all of a sudden I am actually putting 500 kilowatt on the district, on the grid. So which is not very good, because then the grid will actually collapse. So therefore, whenever there is a sudden change in the power demand by the vehicle, it actually comes from the battery, from the storage. Okay, and later on, when no one is there and at night, it will slowly take power from the grid and replenish its energy. Right. So therefore, the storage is actually a major player in all kind of EV infrastructure. They are not there in many systems right now, because right now we don't have a lot of EV in our system. But later on, when we are trying to make it a infrastructure, like common infrastructure, you will require to have this storage there. So this will be grid level storage, like high power storage there. So they are like the shock absorber. All of a sudden, if you require power, then that is actually supplied by this storage. So that will be it. And then of course you can have renewable energy also, and connect it to the system. So if you look at a EV charging infrastructure, there are many layers of control. Like I was talking about this control, right? So this control here, and I was telling you that there is a CCCV control, but there are many layers of control. Like for example, there is one layer that I was talking about, is called the primary layer, which is directly controlling whether it is a CC or CV. But there is also a secondary layer which is actually taking care that all the power that are coming from different sources are actually properly distributed. So that will be the second layer. That will be called a secondary control. Okay, and then there is a tertiary control, where when you go and put your credit card, then actually your charger gets activated, right? So those are a tertiary control. The reason is that actually our credit card information is going to a central place. So there is internet connection there. So this internet connection, RFID, etc. So all this supervisory control that they call it, they will implement it in something called a tertiary control. Right. So these are your 3 levels of control that will be there in your system. Right. So that will kind of conclude my presentation. If you have any questions, I can take it. Okay. So if you have no questions, then I guess I'm done.
Sir, sir,
Yeah.
sir, one question.
Yes.
If is there sir difference between state of charge and state of energy SOE with it come to monitoring the system health?
See, these are all battery related questions you are asking me. I am not the proper person to answer them, but I can just give you some indication that actually state of charge is what we uh, uh, very dynamic, right? Like for example, I want to charge my cell phone. Okay, then that will be like a dynamic thing, right? Every day I charge my cell phone. Now, over a period of time, how much energy is left in my cell phone battery? Like for example, in the first year, my cell phone, a full charge cell phone goes for 1 day. But after 1 year, my full charge cell phone will go for let's say 20 hours only. So that means the state of energy has reduced, right? So state of energy is more a slow phenomena, and state of charge is more a dynamic phenomenon. Dynamic phenomenon is like dependent on right now what is happening. So that much I know, but how do they relate to and why the energy reduces? That is something some battery expert can tell you. I'm just telling you overall what it means.
Hmm. Means they are not the same.
Short term, you think about state of charge, but long term, you think about state of energy, because at some point, 3 years, 4 years, you do replace your cell phone battery or laptop battery, right? So the why it has, because the energy what it was holding in the first year or first day is not the same now. Okay, because it has it's same as us, like getting older, right? Like what how fast I used to run when I was 20 years old and how fast I run now are completely different. I mean, same hand is there, same feet is there. Why am I not able to run? Because I have deteriorated in health. I have become older, right? So that is state of energy, and it's a long term phenomenon. State of charge is a short term phenomenon.
Okay, sir. Thank you, sir. Thank you, sir.
Yes. Any other questions? Okay. Okay. I will log off now, right? Okay. All right. Thank you.